Hello everyone, thank you for watching this video. My name is Rui Zhou, and today I'm going to present our paper, A Theoretical Basis for Practitioners Heuristic 1/n and Long-only Quintile Portfolio. So this is the outline of this presentation. First, I'm going to give the motivation of our paper. Then I will show how to interpret the 1/n and quintile portfolio as a robust portfolio design. Furthermore, I will show how to derive the quintile inverse volatility portfolio. And then I will give the numerical results. First, let's look at the motivation. There actually exists a lot of optimal portfolios. For example, the global maximal return portfolio and global minimal variance portfolio. Because in the industry, the investor will use the mean of the portfolio return as the profit and the mean and the expected variance of the portfolio's return as the risk. So they want to maximize the profit and minimize the risk. The mean variance portfolio and maximum Sharpe ratio portfolio is to strike a balance between the profits and risk. So we can choose any of these portfolios and solve the problem to get the optimal portfolio. But actually, in the industry, the practitioners do not like these optimal portfolios. They prefer another kind of portfolio. It's usually called the heuristic portfolios. For example, the 1/n portfolio. It equally allocates the weights to each asset equally. And the quintile portfolio is to first sort all the assets according to some factors. For example, the estimated expected return. And in this case, the assets with the highest expected return will be ranked at the first place, and the asset with the lowest return will be placed at the bottom position. Then the quintile portfolio will equally long the top 20% assets. So although these heuristic portfolios look very simple and naive, they actually work very well. Here we show the backtest result of SP 500 stocks, and we plot the cumulative return. So this line is the heuristic 1/n portfolio, and this yellow line is the heuristic quintile portfolio. We can see that in this case, the heuristic portfolios defeat the optimal portfolios. That's very interesting. How could that happen? An explanation is that we actually have very poor knowledge of the true parameters like sigma and nu, and some small perturbation on the parameters might lead to a significantly different solution, especially when you have incorrectly estimated new parameter. And that's how it says a tiny mistake will result in a huge one. So if you want to consider the estimation error in the portfolio design, we're actually doing the robust portfolio optimization. But that's not the purpose of our paper. We want to reinterpret the heuristic 1/n and quintile portfolio as a mathematically sound optimal portfolio. So in this paper, we will bridge the gap between the heuristic portfolio and the optimal portfolios. And we will show how to derive the heuristic portfolio through the robust portfolio design. So first, let's look at the mean vector uncertainty set. There exists also a lot of uncertainty sets for the mean vector. For example, the box constraint and the ellipsoid constraint. But neither of them can help our purpose. So in this paper, we propose an L1 non-ball uncertainty set. It says that the true parameter nu is located in L1 known ball around the estimated return of the assets. And the size of the L1 known ball is decided by a parameter called epsilon. And we assume that the elements of the estimated nu have been sorted in non-increasing order. And then we can write the robust maximal return portfolio, which is to maximize the worst case return of the portfolio. And if we can take some, and then we can write this problem into this equivalent form. And this is a convex problem. We have proved in the paper that the optimal solution to the robust maximal return portfolio in this form is like this. So its first m elements are equally weighted, and the number of these elements or the number of these active assets are decided by the estimation error. So it says that the weight allocated to its active asset is exactly the same, and the larger epsilon with more active assets. So from this result, we get the following two corollaries. So if the estimation error is large enough than a threshold, then the optimal solution of the above problem is exactly the 1 over n portfolio. And if the estimation error is not too large and is bounded by some numbers, then we can get the long-only quintile portfolio. So for now, we have already shown how to derive the 1 over n and quintile portfolio from the robust maximal return portfolio. But we might think that this uncertainty set might not be very convincing because it assumes the estimation error can equally affect all elements in the estimated mu. But intuitively, we think that the estimated mu with larger variance should be more likely to suffer large estimation error. So therefore, we think it might be more reasonable to include a variance in mean vector uncertainty set. So here is the proposed variance adjusted uncertainty set. This symbol means the element-wise division. Again, we can write the robust maximal return portfolio problem. We'll maximize the worst case return under the new uncertainty set. And we have also proved in the paper that the optimal solution to the above problem is like this. The first m elements are non-zero, but their weights are inverse proportional to their standard deviation. And the number of these active assets is decided by the estimation error. So now we have shown that the weighted allocated to assets, active assets, is inverse proportion to their standard deviation. And the larger epsilon, the more active assets, very similar to the previous one. And also, if we have the estimation error larger than a threshold, we'll get a portfolio very, very similar to the 1 over n portfolio. The difference is the weight is adjusted according to their standard deviation. And if the epsilon, the estimation error, is bounded by some numbers, then we will get the quintile inverse volatility portfolio, where the first 20% assets will be active, and the weights is inverse proportion to the standard deviation. So now let's look at some numerical results. So in the numerical experiments, we do the backtest over 100 stocks, and we show the median of the conditional value at risk. Basically, this measures the worst case loss of the portfolio, and the smaller the better. So we can see that if we have 20 active assets, that's actually the heuristic long-only quintile portfolio. And if we have 100% active assets, that's the heuristic 1 over n portfolio. But from this picture, we see that neither of the two heuristic portfolios are the best choice for the investors, because the best choice appears when we have 75% active assets. So that's quite interesting result, because it tells us that for the practitioners who choose the heuristic long-only quintile portfolio, they actually underestimate the parameter estimation error. And for the practitioners who choose the heuristic 1 over n portfolio, they actually overestimate the estimation error. And if we can find a vice choice of the estimation error, then we might get a really good profit. So let me summarize the presentation. We have formulated a mathematically meaningful, robust portfolio design problem. And this proposed problem can reduce to the two heuristic portfolio on different uncertainty level of the mean returns. Besides, we have also proposed a variance-adjusted uncertainty set of the mean vector. It derives the quintile inverse volatility portfolio. Thank you.